A very warm welcome, very good morning, good afternoon, good evening to all my dear friends, participants and students for this course under NPTEL MOOC, and the title of which is Application of Forecasting Regression and Time Series Models. And my good name is Raghunandan Sengupta from the IME department at IIT Kanpur. So, as you all know, and by this time all these three informations is absolutely ingrained in your mind. The first major topic under this course is forecasting, second one is regression, third one is time series. And as you are aware, we are covering the concepts and ideas of regression models. This is week number 8, lecture number 40, which means by the end of this lecture, we would finish 8 weeks of class, and then another 4 weeks will be remaining, considering it's a 12-week course, which actually is 30 hours and 60 lectures, each lecture being for half an hour. What is the coverage for this 40th lecture? We will cover LINEX loss functions in more details. We have done that. We will cover more details with problems. We will consider what we mean by expected value of a loss for overestimation, underestimation, for regression, for estimation, for prediction. What do you mean by loss? And we will also consider the concept of risk of estimation, because as we will see later, expected value of loss is necessary because the loss would depend on the estimate which you find out. So, if you have a sample, each time the sample set of observation will change. So, as it changes, the overall estimate which you want to get from the sample and which you want to compare with the parameter, the estimate will change. As it changes, it will have a particular distribution. I am not going to go into the distribution concept. As it will change, let me continue talking about that. As it changes, it will have a distribution, and for that distribution, you will actually have an expected value. That expected value of the estimate, if it is unbiased, is equal to the parameter, which we have already seen for the case of beta hat being expected value being equal to beta. And when we want to find out the loss actually means, in the concept of ordinary least square, it is actually the square of all the summation of all the losses or the errors, and as the estimate is changing, as I mentioned, it will have that whole term, expected value of the loss would be there, and that we term as a risk. So, risk would be considered as a measure or as an idea which will give you a huge amount of set of information that the estimate which you are trying to utilize, how good or bad it is with respect to the parameter which we are trying to find out. Now, the concept of estimation of the loss is also there in the concept of unbiasedness. So, technically is a way of trying to check the unbiasedness of that estimate or some function of the estimate. Why it is required? I had started discussing that in the 39th lecture. I will go in further details in this 40th lecture. So, if you remember the 39th lecture, we were discussing the following. So, consider we have already found out beta hat using the actual estimate of the OLS. Then, based on the fact that L, I will use a different color here, L is a vector of constant, and we actually find L into beta hat with the corresponding concept that row and column multiplication is feasible, we will get the value of theta which we are trying to study, and actually as beta hat is there, hence it will be theta hat. And I also mentioned the expected value of theta hat in the long run would be equal to the value of theta, that means unbiasedness would also hold true. Now consider L is equal to all the values, because as there are 4 beta, beta naught hat, beta 1 hat, beta 2 hat, beta 3 hat. So, we have L as either, depending on how you nomenclature it, it will be 4 by 1 or 1 by 4, the column vector or a row vector. When we multiply the values of that L into beta hat is already known. If you remember, we are taking from the problem where we are trying to find out the return of Tata Motors given NSE 50 returns, and the time frame is from February, March, April, May, June 2025. The other two independent variables x 2 and x 3 are the corresponding rupee to Indian to US dollar in Indian rupees and Brent crude price in euros. And based on that, when we find out theta hat, it comes out to be 1.0404560. We have already mentioned that. Now, what we do is that we take the value and find out theta hat for the case when it is squared error loss, and we also find theta hat when we utilize the LINEX loss. That those corresponding values are given in the second column, which I am marking, and the third column. Second column values will not change because the concept of LINEX loss is not there. So, the corresponding values for different of theta hat for different values of A remain the same, which is 1.0456. When we utilize the formula for theta hat LINEX, the formula is already given in the last 39th lecture slides. Depending on the value of A as minus or A as plus, the third column values are the corresponding values for theta hat LINEX as A changes. So, we are trying to compare. What is interesting is to note the fourth column, which gives you the difference between theta hat squared error and theta hat LINEX. And very interestingly, 3 important points. Number 1, which I have already mentioned, but I will still repeat. Number 1 is when A is 0, then the value of theta hat squared error loss and theta hat LINEX are the same, because A is 0. So, that whole component which is coming from the concept of LINEX loss adds no value. So, hence both the values are plus 1.0456, where I am putting the tick mark in violet. But if we see for negative A and positive A, the values of theta hat LINEX are different. So, if I consider the value of negative 1 minus 1 for A, then the value of theta hat LINEX comes out to be, I will put, say for example, the orange tick mark, it is plus 1.8256 and the difference comes out to be minus 0.7801. And if I take the other extreme, when A is plus 1, when I am putting blue tick mark, the value of theta hat LINEX comes out to be plus 0.2655 and the difference comes out to be plus 0.7801. So, very interestingly, a quick look at the difference values gives you an idea that overestimation and underestimation for theta hat LINEX are portrayed depending on the value of A. That is point 1. And point number 2, as it is a function of A only, which is linear, hence the difference for minus 1 value of A and for plus 1 value of A, the difference quantum wise are same, which is 0.7801, but with a positive and negative sign depending on whether A is positive or A is negative. Now, if I plot it, and what do I plot? I plot the values of A along the x axis, which I will mark here. So, A are all positive on the first quadrant, A values are all negative in the second quadrant, and the blue horizontal line which you have, which is this one, is the value of theta hat squared error, because A does not have an effect on theta hat squared error loss. But when I put and utilize the value of theta hat LINEX, as theta hat LINEX is a linear function of A, you see very interestingly the value of theta hat LINEX is like this. That means, it gives you a very clear cut idea that how overestimation and underestimation can be considered using the concept of LINEX loss. Now, if you remember, I did also mention that what we are taking here, I will just verify before I go to the next point. So, this is the plot of theta hat LINEX squared error and theta hat LINEX against the parameter A value, which I just discussed. Now, the idea, if you remember, which I have said or mentioned, that you are trying to you cannot compare apples and oranges, which means that if someone is suffering from fever, then it is best to give a medicine which will alleviate fever. Somebody is suffering from stomach upset, the medicine should be actually be just for stomach upset. So, trying to give a medicine when the disease or the symptoms are different, it does really give some relief, but the amount or the quantum of relief is not that much if the right medicine is not used. Which means that under the environment, when you are considering squared error loss, the LINEX loss parameter or the estimate may not give you the right amount of risk to that quantum what you want, to the low value. Similarly, when the environment is LINEX, trying to utilize the squared error estimate of theta hat may not give you the right quantum of risk, that means to the lowest value, and we will see that further on with more such calculations. Now, another thing which I also mentioned, that why are we considering theta hat, in the sense that we take L values as, or it is either a 4 cross 1 or a 1 cross 4 vector, and then multiply L with beta hat and find out theta hat. The answer why we are doing that will come up in the subsequent slides. Now, consider L as not all values are 1, consider it is 1 0 0 0, which means when I multiply this L value with beta hat, I will only get the value of theta hat, which is actually equal to beta naught hat, as you see here. Which means that in a very simple way, considering that we have the formula for theta hat, and both for the squared error as well as for the LINEX case, we can substitute the value of L accordingly, such that we are able to get all the corresponding values of beta naught hat, beta 1 hat, beta 2 hat and beta 3 hat, and that is what we are doing. Considering A values are given in the first column, beta naught squared error values are given in the second column, beta naught LINEX values are given in the third column, and the fourth column gives you the difference. So, obviously, the second column values, all values should be independent of A, and the values, as you see, is actually minus 0.19940, this one. Now, considering beta naught LINEX, if you put in that formula with the LINEX concept being there, you see very interestingly the values of beta naught LINEX are given in the third column. And when I find out the differences, again 3 important similar facts come out. Point 1 is for a value of A is equal to 0, both beta hat squared error and beta hat LINEX are the same, as it should be, no confusion. And for values of A positive and A negative, you see the quantum of the difference between squared error estimate of beta naught and LINEX lot estimate of beta naught, the quantum is same, but with the opposite sign depending on the value of A, which gives you an idea that how to find out only beta naught under two environments, you are able to portray the concept of overestimation and underestimation. Similarly, we switch our attention to find out beta 1 hat, which means that we replace L value as 0, 1, 0, 0. When we multiply that with beta hat, we get theta hat as equal to beta 1 hat, which is plus 1.2410. We again do the same thing, find out the first column gives the value of A, second column gives the value which is constant everywhere, beta 1 under squared error environment, third column gives the beta 1 hat under the LINEX loss environment, and the fourth column gives the difference. So, the three facts which I will put a tick mark and which are obvious, both the values are same for A is equal to 0. Overestimation and underestimation are unequally penalized in the sense for plus A and minus A, the quantum of difference remain the same, but with a positive or a negative sign depending on A being positive or negative. Again, we are able to find underestimation and overestimation of beta 1 hat. So, you have done that for beta naught hat, we have done it for beta 1 hat. So, now we go to find out correspondingly for beta 2 hat. We find out L, replace it as now as 0, 0, 1, 0, multiply that with beta hat what we have already found out under the squared error environment, theta hat comes out to be, which I just circled, plus 0.00310, the first, second, third, fourth column are same, in the sense what we have done it and seen it in the last slides. Again, for same value of A being positive and negative, beta 2 hat LINEX is overestimated or underestimated, but the quantum remain the same. That is again interesting fact. Even, and remember the quantum here for values of minus 0.75 and minus 1.0, because the values are so small, I have only taken 4 places of decimal, hence the differences are the same. But the signs are different depending on the values of A being positive or negative. So, again you get separately the LINEX loss environment or the case and find out what is beta 2 hat under different LINEX loss or the ordinary square. Finally, we go to beta hat 3, put L as 0, 0, 0, 1, multiply with beta hat, get theta hat as beta hat 3, which is plus 0.00090. Again, we have the same columns as with A, beta hat 3 squared error, beta hat 3 LINEX difference. Now, the difference which you see are all zeros because we are only taking 4 places of decimal. So, if you take of 8 or 9 places of decimal, the actual concept which I am saying that for value of A is 0, both the squared error and the LINEX loss estimate are same, which we have already found, and the differences would be positive or negative depending on the value of A as positive or negative, and the quantum of the difference remains the same for, say for example, A plus 0.75 or A as minus 0.75. So, with this we are able to find out the beta values which are the regression coefficient for the environment which is squared error. We are also able to find out beta hat under the LINEX loss environment. We have compared them, we are aware the concept of overestimation and underestimation, and you can utilize that very safely when we want to solve the problem for predicting y hat values under the environment that you are taking either the squared error or the LINEX loss. That means, very simply by solving beta values individually, we get the LINEX loss environment beta values and can utilize both. Again, I am repeating, the beta under the squared error environment, beta under the LINEX loss environment, and we are able to compare the estimate or the prediction values of y values, yi values with the yi hat values, and that will give us the error. And the error which we have found out, considering it is ordinary least square, we have mentioned and we have assumed 0 mean, fixed variance. We can also check what are the properties for that error under the LINEX loss environment. That would be an interesting way to compare. Now, what I have been talking about, that under the environment of LINEX and squared error, you get two different estimates and they give you two different answers, which you have already seen in the subsequent previous slides. But what does this slide actually denote? And this is what I had mentioned last day in the 39th lecture, which I had mentioned today also in the 40th lecture. Environment being LINEX, and if we are utilizing squared error estimate, or if the environment is squared error and you are utilizing the LINEX, then the expected value of the loss would not be optimal, which is exactly the same statement which I made. You have fever or some person has fever, taking stomach upset medicine or vice versa may relieve the pain or the level of uncomfortableness. But remember, you have to basically utilize the right medicine for the right infection, which means for the right environment or the loss you use the right estimate, and this is what is being portrayed. So, what is portrayed is as this: if the environment is LINEX, which I am highlighting in blue, and if you are using the estimate at squared error, then the expected value of the loss, which is the risk, is given by this. Again, I am repeating, environment is LINEX, you are utilizing the squared error estimate, the expected value of the loss or the risk is given by what we have highlighted in blue. Similarly, the question may be asked by many of the candidates or people who are curious, if the environment is squared error and the estimate you are using LINEX, are we able to get the expected value of the loss or the risk? Answer is yes. Will it be different? Answer is yes. I have not gone into that much detail. Similarly, when the environment is LINEX and you are utilizing the LINEX estimate, or the environment is squared error and you are utilizing the squared error estimate, again you can find out the expected loss for both these conditions and the risk would be different. So, technically you can find out, depending on the environment, depending on what estimate you are using, you can find out 4 different values of risk and you can compare them, which I will try to do not in that detail, but some comparison would be done. Now, if the environment, let me mark, if the environment is LINEX and the estimate which you are using is also LINEX, then the overall expected value of the loss or the risk comes out to be this. This is equation, but you may be thinking it's so complicated. Answer is it's not at all complicated. If you look at here, there are a few very interesting facts. The fact 1, and I will mark them with different colors. Fact 1 is that n minus k by 2 or n minus k by 2, or more specifically n minus k remains, which is actually the number of observations for y and x minus k, which is the number of different independent variables. That is the loss of degrees of freedom, point 1. Point number 2 is that this value which you have, I will use a different color, say for example green. The value which you have here is always known to you, because if you remember, you have found out beta hat, I am using the black color, is equal to, which you have found out is x transpose x inverse into x into y. Let me check your, let me check the dimension. So, that means they should not be in confusion. This is n cross 1, this should be k cross n, and this whole value should be k cross k. So, if this is k cross k, technically this should be transpose. So, x transpose is k cross n, x is n cross k. So, inside the bracket is k cross n into n cross k is k cross k. Outside you have k cross k into k cross n gives you k cross n, and k cross n into n cross 1 gives you k cross 1, which is the dimension of beta hat. So, this value which you see here, you already know. You have been doing it for such a long time. And sigma square, what is it? It is basically, we have already said that few times, it is the variance or variability of the error. And considering the concept of, again I am mentioning, sorry for that repetition, the concept of homoscedasticity, heteroscedasticity, autocorrelation, non-autocorrelation, those points should be taken care in this LINEX loss environment also, when you are trying to fit in the multiple linear regression model. And a value is known. If you remember, there were two parameters in the LINEX loss, scale and shape. And this value of a we have considered for different instances starting from minus 1.0 to plus 1.0. Having said that, the overall formula looks, again I am saying it may look ominous, but it is not that. You have all the informations, and based on that we will try to compare, as you see here in this slide. It is LINEX loss environment, you are utilizing the LINEX loss estimate. The earlier one, LINEX loss environment, you were using the squared error estimate. So, now is the time to compare that, given the environment is same, if we use two different estimates, how do the answers compare? With this, I will end this 40th class and continue more such discussion about different loss functions and go into the discussions for the case of balanced loss function later on. And balanced loss function is the term which I am using for the first time. It will make sense how we compare and combine the LINEX loss and the squared error loss to get a new type of loss function, which is balanced loss function, which gives us very interesting results in the case of multiple linear regression. With this, I will end this class. Thank you very much and have a nice day.